So
okay,
let me.
so our next speaker is Damiano Testa from Warwick, and he will tell us about mathematical insights coming from formalization.
Yeah, so thank you very much for the chance to speak. So let me begin. So in case you do not know me, so I'm mostly an algebraic geometer, and I like problems coming from number theory. So this is my background. I really don't consider us having a lot of sort of computational background before coming to the summer. So I use the computer mostly for browsing the internet and writing papers. And in the last few years, I started using a computer algebra system called Magma. So I got familiar a little bit with using a computer to do maths, but it was mostly for doing computations rather than checking proofs or anything like this. So it felt very interesting, but very foreign to me, to the idea of formalizing mathematics. However, I know Kevin, and I knew that he was involved in formalizing math and sort of making people aware that this is what he thought was a good idea. And I was really curious about this. And so this summer I decided to give it a try, and I'm still here and I'm still liking it. So I'm enjoying the process. However, because I feel like I'm very, very young in this, what I say in the future may not sound very reasonable or correct or anything. So please, if you have questions, stop me and ask, because I may be saying things that you're very familiar with, but in a way that doesn't really align with what people usually say. Okay. So again, as a disclaimer, I'm comfortable with the mathematics of what I'm going to be talking about, but the formalization side is much less comfortable for me. And I'm going to be talking about
Damiano.
Yeah.
Do you think you can move a bit closer to your mic? Because
yes.
It sounds like.
I don't think this is a problem.
Is it better now?
I think the connection is not great.
Oh.
Let me see if I can close some more windows. Did it get better? Can you hear me?
This sounds great.
Okay, so all right. So I'll continue, but do let me know in case you have problems listening to what I say.
Except we can't do anything.
Yeah, I could try speaking slower. Oh, I can switch off my video feed. Sorry, not the screen, but my video.
Oh, that would probably help, yeah.
Okay, so anyway, so also I feel that what I want to formalize is interesting, but what I have formalized is trivial. Maybe this is a common shared experience from everyone here, but I feel it applies particularly in my case. Okay, so so let me begin. So what I really decided that I wanted to formalize was the theorem of Chevalier, and it's something about algebraic geometry. So don't worry if you don't understand the statement. I will comment more about this, but it's not particularly important what it is about. But the statement essentially says that if you have a morphism of schemes, then the image of a constructible subset of X is constructible in Y. Okay, so basically this is saying you have a function between two topological spaces, and you have some nice topological subspaces of X, and you can say that their images in Y are also nice. This is a very sort of coarse way of looking at this. And as an algebraic geometer, I find this is a very important statement, and it's a very useful statement, and so I decided that I wanted to formalize this. Okay. So here I copied the statement at the beginning, and so just like you would do in a mathematical proof, you kind of have some initial reductions, and so you first want to say, well, X and Y can be basically anything at all, but actually it suffices to prove this statement when X and Y are somehow special. And so if you can see here, the first reduction is you can suppose that X is just the product of Y with affine space. So if you're used to maybe more topological considerations or algebraic topology, you can think of X as being a fiber bundle over Y, or maybe even a vector bundle over Y. And by shrinking your sets further, you can make sure that the vector bundle is trivial. And so you really have a product of Y with something else. And on the algebra side, this means that you're going to use a commutative ring, which stands for Y. And you want to study the inclusion of this commutative ring inside the polynomial ring in our variables. And you want to say something about this inclusion. And in fact, by induction on R, you also reduce to the case in which R is equal to 1. So you really are just interested about the product of Y with a line and mapping down to Y. So this is just the projection onto the first factor. And you want to say something about some subsets in the product. How do they map into Y alone? And so this is the setup for the statement on the mean side. So we have a commutative ring R, and we're looking at the constant map that takes the ring into the constant polynomials with coefficients in that ring. I haven't said what the statement is yet, and I won't say much about it, but basically it's some statement about ideals on either side and how they correspond to one another. So the simplified version of Chevalier's theorem, taking into account all of these reductions, is that so we have this projection from Y cross A1 onto A1. This is just the projection onto the first factor. We have two open subsets inside the product. And we want to look at the image under the projection of the first open set intersected with the complement of the other one. So basically, we're taking an open and a closed set, we're intersecting them, we're looking at its image, and we want this image to be constructible. Now, constructible means it's a finite union of sets that look like this. So it's a finite union of intersections of open and closed sets. So imagine you can do the operations that you normally do on a topology, except you only allow finite unions and finite intersections, but you're allowed to mix out open and closed sets. So this is what you want to show. So you want to show that this image is of this form. Okay. So now look that we have always open and closed things, and we're looking at their images having to be open and closed, or intersections of unions of open and closed things. And it turns out that in our special situation, the map here, you can prove in math that it is open. Okay, so this simplifies the statement that we're trying to make, because if we can prove that the map is open, so that's one of the things we want to show. And the other thing is we want to show that if we have a closed subset in the product, then the image is constructible. Notice it won't be closed in general. You really need constructible, but you can think that closed might be a good approximation. So then this suffices to prove what we want. Okay, so these are still reductions of our general statement to a very, very concrete or very special kind of statement.
Damiano, maybe if there are people who are not familiar at all with this algebraic geometry, you could draw a picture where, in the case where Y is R and A1 is R, and the closed set is the hyperbola x times y equals 1 or something like this.
Okay, so let me try to do this. So this is the eraser.
I know that algebraic geometers are not allowed to draw pictures usually, but we won't.
Yeah, you're completely right. So except I don't see erase drawing. Oh, I just click on these colors and I can draw.
Maybe.
Yeah. All right. So imagine that this is what I've been calling Y, and this is the vertical direction is the one that I've been calling A1. Okay. So in this case, these are two copies of A1. And we want to look at closed subsets in here and how they project onto the Y, onto the coordinate that I've called Y. Okay, so sorry about the notation. Maybe I should have called X. I didn't realize I was going to draw this. So in any case, if I look at the subset X times Y equals 1,
yeah.
So we all know that this subset, maybe I'll draw it in different color, maybe in blue. So this one looks like this. Okay. So this subset is certainly closed in the product, in the plane. It's given by a single polynomial equation, so it's given by a C-infinity function, so it's certainly closed. But when I project it onto the horizontal axis, I look at the points that I get everything except for the origin. Okay? So I get an open set, but not a closed set. Okay? So I get a set that is constructible, but not a set that is closed. Okay? And this is really the heart of the matter, of what goes wrong into saying that the projection is closed. Okay? So the projection is not closed, but nevertheless, the image of closed sets is always constructible. Okay, so constructible means it's a finite union of intersections of open and closed sets. In this case, it's just an open set. Okay, so intersection of everything with, of an open set with univ, speaking sort of in lean speak. Okay, so are there any more questions, or is this clarified a little bit what's going on? Okay. Whereas with open,
what did you to say?
Okay, perfect. Okay, so let me continue then. Okay, so this is then a summary of what we reduce the statement to be and what I have been able to do. So we are in this projection, so we have this sort of xy plane and the projection onto one of the coordinates. We want to show that the morphism is open. This is something that mathematically I know is true, but I didn't know it was actually true also in lean until a little while ago. And then I want to show that the image of a closed set is constructed. So as I said, I've been able to fully formalize one. So that statement is not just apparently true, but it's actually true. And item 2 is still in progress. So I'm going to be focusing a little bit about what happened in item 1, and I won't say much, in fact, anything at all about item 2 unless you ask me. Okay, so before I go on, let me show you what the proof looks like. Because I started working on this and I produced this and this and this, and this is what the proof actually looks like. Okay, so I thought it was short and I was kind of happy with this, but it was turned out that this was way too long for what people usually like in MathLib. So I just put it here because I like to show big things, and this was something that was big. You can see that my cursor is down at the back here. The statement was maybe a couple of pages before. It was statement disappeared. Well, the statement is probably up here somewhere, and it's a statement that the map is open, and you see goals accomplished when you're down here. So everyone should be happy.
So sorry, what's the statement look like in lean?
The statement is actually, I'm really sorry that it's not showing, but the statement is open map of, so let me go back to here.
I mean,
so
does it involve products of, we don't have products of schemes. This is what I really am interested in.
No, but there is the spectrum of the polynomial ring. And there is a map induced from a morphism of rings. There is an induced map in spectra.
Sure. Oh, I see. So you've only proved it if Y is affine.
Indeed, but a scheme is covered by affines.
Sure.
Yeah. So
but the product object doesn't exist. That's all. You don't have products of schemes.
Sorry. So maybe I'll go back to here. So in this context, there is a prime spectrum of the polynomial ring and the prime spectrum.
I see.
And
so
there
you've just proved it for affine schemes.
Indeed.
I see. Then that's fine. Then I get it.
Okay. So the statement is, sorry, maybe I'll just go back to here. So the statement is that the induced map on schemes associated to C is open. Okay, so that's the statement that whose proof occupies those pages that you've seen before. So this, as I said, is the proof. So after having proved this, I learned about Golfing. So I asked a lot of questions on Zulib. I received a lot of comments, and I'm very, very grateful for the Zulib chat. So I want to take this chance to thank everyone on Zulib for helping with all of the silly questions that I posted there. And so after playing a bit these simplifications, this is what the proof shrunk down to. Okay, so before it was approximately 250 lines, now it's approximately 90 lines. So now it fits in the, oh, in fact, now here you can see, so this is the statement. So, so this is the statement that ends here.
I've put my glasses on.
Yeah, sorry, I printed small so that it would fit in a page. I can share the code if you want.
I see. Is open map. Yes, yeah. Great.
Okay, so of course there's room for further compression, there's room for changing the names. And so I want to talk a little bit about what I believe is going to be a better way, sorry, not a better way, but a further way of compressing this proof. So at the beginning, when I started talking about this project, I simply went through some mathematical steps that would simplify the proof, the way in which I would formalize a proof in math. In fact, those steps were basically taken from the Stacks project. And what you see here is essentially a translation of lemma 10.28.7 of the Stacks project. And the statements in the Stacks project are very easy to read for a human. But it turns out that they were pretty hard for me to formalize as stated. And so the result was that the argument was very long. At least my version of it was very long. And the simplification that went from the 250 lines to 90 lines was basically sort of shrinking further this proof, but by going around the same steps that the proof went, just making them more efficiently. So this kind of looks to me like a meandering river or a plane filling curve, where in math you have lots of steps where you say, oh, we're used to this, or we're used to that, I can assume that, I can assume this, where you're basically not doing anything. You're just sort of getting your head around what it is that you need to do. And then eventually you prove something, and then you kind of unwind everything that you did. So you want to go from here, you need to go there, and this is the path that you find. Okay, so you could have just gone like this, but you don't. But this is something that happened that I was very familiar with in math, except that when you're formalizing things, you really don't want to go around like this. You just want to go straight. So why does this happen? So for me, when I think of a mathematical problem, actually the plane filling proof that I find is in some sense essential for convincing myself that this is actually a proof of something true. So all of these steps that I take here are lemmas and examples and detours and related results that are not necessarily needed for the statement, but that slowly convince me that what I'm doing is actually true. Maybe I'm not finding an actual proof, but because there are so many things around that are true and that are consistently compatible with everything that I see, eventually I get to a stage where I know that what I'm trying to prove is actually true. And then I set down to actually write down the proof. Okay, so this is at least in my mind, this is why you need this carpet of examples and lemmas and various things. Now, when I learned how to formalize things, I realized that people in the Lean community call this the API. And so now I realize that the API is basically this carpet, but done on a computer, so that the computer can take care of all of the meandering around. And you just have to focus on actually stringing these things together in the most efficient way once you have enough of these lemmas. And so what I really think should be done in this proof is sort of to look back at the proof and try to, without an eye towards formalizing it, and then after that write the actual proof. And so what I let me see how many times, a couple minutes. So so this is sort of iterating what I said. So when I'm writing a mathematical paper and I set out to write something, I'm fairly confident what I'm trying to prove is true because of this carpet. I'm also confident that I will probably make mistakes when I write it down. However, I'm not particularly worried about the mistakes that I make because I know that all of these extra lemmas and extra arguments that I have will be able to sort of overcome all the difficulties that I will come because I thought about it for a long time. Now with Lean, the situation is a little different. You still have to create the carpet, but you do it for different reasons so that the computer can check all of these things for you. So this is my understanding at the moment of how things go. So now if I go back to the statement, this was the statement that Kevin asked about. So this is what you want to show is open. In fact, eventually this satisfies Chevalier's theorem. And so it turns out that the main property that this needs is the statement that is written here about ideals in a polynomial ring. So I won't actually go into the details because I'm running out of time. But basically, this statement here, which says that if you have a polynomial in a polynomial ring, and you have an ideal in this polynomial ring, then this polynomial is contained in this ideal. Sorry, the ideal is just in the base of the polynomial ring in R. You have a polynomial over that ring. You want to know that if the ideal generated by I inside the polynomial ring contains F, then the coefficients of F must belong to the ideal. This is kind of, and conversely. Okay, so this is the if and only if statement that you really need. And it turns out that this statement does happen in MathLib, and it's already there. So this is the MathLib version of the statement that is written here. And I hadn't really realized that this was the heart of the statement of the openness of Chevalier's theorem. So, and if you go back to the proof, you realize that this mem map C if and only if appears, but just at the very last two lines of my proof. Whereas I think that by expanding this lemma into making it more visible, I think the proof will be much simpler because this is really the heart of the problem. But what I hadn't realized that this was the heart of the problem when reading the mathematical paper. So I was just, I kind of followed the argument along. I went along the river and I strolled around, but I didn't realize that this was where everything was happening. So. So what I think is that I will have to go back and sort of redo the proof, but by expanding this mem map C if and only if to make it work, and then this is probably going to be a shorter proof and something that can that I would feel more comfortable into posting into MathLib. All right, so that's it for me. Thank you very much.
Thank you, Damiano. Do we have any questions?
Just a comment, I guess. I think that at some point we're going to have to prove that the product of two schemes is a scheme. So
sure.
And then once one has done that, one has to ask whether, you know, this result we have here for affine schemes can somehow be translated over. You know, what a good test for products. I mean, constructing products is already hard work, but a good test for them would be to see if stuff like this can easily be ported over. You prove things in the affine case, and then you deduce it in the general case by gluing. But gluing can be hard. What I'm saying is moving from the affine case to the general case might not be as easy as one might imagine.
So again, I don't have a lot of experience in formalization, but I'm starting to realize that things that look completely trivial in math become very difficult when formalizing things. In the mathematical side, this is really just a statement that every point is an open neighborhood, which is affine. Whether this is actually easy to implement with the definition of schemes, I don't know, because I've only really played with the prime spectrum. So really only played around with affine schemes. I don't know how hard it is to get open affine neighborhoods of points and schemes in general.
It shouldn't be too hard, but yeah, I haven't really thought about how to formalize products of schemes. We'll have to get to that at some point, but I guess, I mean, proving Chevalier's theorem in the affine case is going to be the heart of that proof. So I wouldn't worry about it too much for now. I really liked the last slides of your talk. These, or well, like this meandering river stuff. It's it put some pieces of a puzzle in my head into place. So thanks a lot for that.
No, no problem. I really always feel that I'm moving along a sort of plain filling curve when I'm proving things. And so
Yeah, but explaining that basically now you have to do that, but you call it an API. I think that's a really nice observation.
thank you.
Great. So maybe we'll have more algebraic geometry questions during the next break, but we can move on to the